So the non-crisp information is a more general kind of framework. It allows us to create, target more general kind of desiderata. So in particular, it turns out that some of those natural subclass of such desiderata also automatically imply optimal behavior in Newcombian problems, or in most Newcombian problems. There's some conditioning that needs to hold. So first, let's start with an example of XOR Blackmail. So I claim that we can describe this example as a non-crisp ultra quantity. So how would we do this? Okay, let's say that there are like two states, S0 plus and S0 minus. And our initial ultra distribution is ambiguous between both of those, right? So it's like that. It's like take delta S0 plus and delta on S0 minus, take the convex hull, and then take the downwards closure. Like this. And now, right, and now there's either termites or no termites. So let's say that this is we'll call it S1 plus, and this is S1 plus prime. And this corresponds to termites, this corresponds to no termites, and this is 99%, this is 1%. And this is like S1 minus, S prime minus. And now, and also, when we go here, there is an observation of blackmail, and here it's no blackmail, and here it's no blackmail, and here it's blackmail. Okay? So when it's blackmail, we can either accept the blackmail or reject the blackmail. So here, if we accept the blackmail, we get into some state, let's call it, so we have accepted the blackmail, so it's some state S2, S2 blackmail, blackmail. So this is accept. But when we reject the blackmail, then the transition kernel outputs 0. So now the transition kernel can output a contribution. Doesn't have to output a distribution. Right? So it can just output 0, like 0 contribution. Here, there is no blackmail, and okay, it doesn't matter which action you take, because there's no blackmail anyway. You get to a state with termites, T. Here, there's no blackmail, and there's no termites, so here there's some state where everything is good. Let's call it STG. And here there is blackmail. So if we reject it, we get into the state with termites. But if we accept it, then the transition probability is 0. And now, from those states, from all of those 3 states, we can go back into one of those, and here there's ambiguity. So we can go to either one of those. Okay? So now this ultra-pond DP has an interesting property that for your policy to get optimal loss with respect to this ultra-pond DP, it has to be rejecting the blackmail. Why? Because if you accept the blackmail, right? If you accept the blackmail, then the call policy will choose. So the call policy can choose whether to go here or go here. So if you decide to accept the blackmail, the call policy will go here. And then 99% of the time you get blackmailed, and you accept it, because by assumption you accept it. So you end up with this state, which has a big loss, because you ended up paying the blackmail. So this is bad. But if you reject the blackmail, so like with 99% probability you will end up here, with 1% probability you will end up here. 99% probability to pay blackmail, 1% probability get termites. If you reject the blackmail, then the call policy, then what would the call policy do? Call policy can decide, okay, I will still go here, despite the fact that you rejected the blackmail. But then what will happen? Then once you arrive here, and you reject, you get 0. So this means your loss will be 0. It will be a really low loss, so everything is great. On the other hand, if the call policy goes here, then with 99% probability you don't get blackmail and everything is good. With 1% probability you will go here and get termites. So 99% probability good, 1% termites. Right. So the optimal policy is clearly rejecting the blackmail. This is the only optimal policy. So anything that has low regret for this ultra-pond DP will have to reject the blackmail. And other than that, this ultra-bound DP is compatible with everything that happens in this game. So it's not like it's falsified in some sense, something like that. So it means that any learning algorithm satisfies some red bound and it has this ultra-bound DP inside its hypothesis space. For example, it's a learning algorithm for some family of ultra-bound DPs, and this is inside the family. Any such algorithm would have to converge to rejecting the Blackmail XOR Blackmail. Now we can do the same thing for counterfactual mugging. So also we'll have like the initial state is like S0 plus equal to minus something. And now there is heads and tails. Heads and tails. And now if there is heads, then you need the mugger. So you need to decide whether to pay or not pay, right? So what happens here is if you pay, if you pay the mugger, not to be confused with reverse system. So if you pay the mugger, you end up in some state, which is the state in which you pay. But if you don't pay the mugger, then you don't end up in any state, but instead the transition kernel here is just 0. There's no state here. Here, the transition kernel of A is 0. But this, you end up in a state of green. But now here, you get to a state of, like, we could just directly say here, you end up with some state of no money, whereas here, so you get a state of $1,000. And again from here and here and here and here, you can go either here or here. So now the optional policy is to pay the mugger. Why? Because if you won't pay, the call policy will choose to go here, and then every time the coin lands on tails, you'll end up with 0 money. Whereas if you choose to pay, the call policy cannot go here, because then with a large percent of the cases you will get plus 0. So notice that this thing happens repeatedly, right? So if the call policy chooses here, it might lock out and you will end up here. But in 50% of the cases this happens. So if your time horizon is long, then the probability approach is 1, you will fall into this, right? So the call policy has to go here if you get paid. And this means that in 50% of the cases you'll get 1. I mean, it doesn't have to go, but if it goes here, then the loss is very small. It's very close to 0. There's a very high probability it will eventually go down. So the uphill policy is paying the mugger. So again, if this ultra-poly P is in the family of hypotheses that are going on with gas, then on the counterfactual mugging, it has to converge to paying the mugger and therefore getting the optimal reward from the anti-mugger. Right? So where does this fail? So let's now consider an example where this method doesn't work. So this example is, or it's a subset of transparent Newcomb. So what is transparent Newcomb? Now we're like Newcomb's problem, but we can actually see the contents of both boxes. The boxes are made of glass. Okay. Okay, but now there's different types of transparent Newcomb. Like the simplest types, the simplest subtypes of this are the kind of empty box, dependent, and the full box dependent. Because now omega has to simulate you, so it simulates you seeing an empty box, or it simulates you seeing a full box. Right? It's like those are like two different scenarios. So if omega simulates you seeing an empty box, then there's no problem. Everything is fine. Because, well, basically the same kind of technique as before works. So you have like S0 one box and S0 two box, and now if you are in S0 one box, then you see a full box. Okay, you see F, which means a full box. And now you get to choose over, now you can choose over one box or two boxes. So one box and two boxes. And here, this goes to an empty. Here you see an empty box. And you can choose over one box or two boxes. And now, so this is the empty box dependent. So if you see an empty box and decide to one box, then here the transition kernel will just stay, reset kernel will just be 0. Whereas if you saw an empty box, you chose the two box, so you got like a reward of 1,000, right? 1 key. Whereas here you saw the full box, so if you want box, you get 1 million. 2 box, you get 1 million plus 1,000. Right. And of course, all of the states go back here. So here there's no problem. Here the uphill policy is again to one box, because like because once you one box, the co-policy, you kind of prevent the co-policy from thinking you 0. right? Because if the call policy will send you here, you one box, then you will be happy. So the worst case will be when the call policy sends you here, and you one box, so you end up here. So here everything is fine. Here everything is not fine. So why? But let's try to just repeat the same trick and see why would it fail, right? So let's try to repeat the same trick. So we have S0, 1, S0, 2. So now one box, so you have to see the full box. Then you have to see empty box. Now it's full box dependent. Now it's full box dependent. So now in the full box, if you see a full box and then two boxes, it makes more sense. So here the condition kernel of E2 is 0. Whereas here you just one box and you end up with your million. Here, one box, you end up with showing nothing. Yes, nothing. And if you like two box, you end up with one box. And of course, it's just those things exams. Okay, so this time it doesn't work. Why it doesn't work? Because, okay, you want to one box in order to earn your 1 million, right? But the call policy can choose to go here. Call policy goes here, and like you're stuck here, you end up, so you're just looking for this part, never end up here. So your one boxing doesn't help you anything. You haven't achieved anything with one boxing. So here this method doesn't work anymore.
So it seems like, in general, you get good behavior if, conditional on you being mispredicted, you could, with high probability, enter the situation where you're mispredicted and actually prove it wrong.
Yeah. It's not even high probability. So we could have, notice this is kind of a fragile, because if we perturbed it, if we imagine there's some probability epsilon of, if you were in a situation where, like, sometimes you randomly show that you have to, like, there's some probability 1% where you're shown you're shown the full box, okay? No matter what you do, then the trick would start working again. So for any probability, no matter how low, for lower probabilities, the time discount would have to be higher in order for this trick to work. But in the limit of gamma goes to 1, it would work for any epsilon probability of, like, randomly seeing the full box. But if there's no perturbation at all, but this is like completely deterministic, then it just doesn't work.
Yeah, I don't know. So what's the difference between the two sides? Why do we draw different diagrams?
So this is the empty box dependent transparent Newcomb, and this is the full box dependent transparent Newcomb. So in the empty box dependent transparent Newcomb, omega simulates what you would do if you've seen an empty box, and then according to that, it either fills the box or leaves it empty. Right? Here, omega simulates what you would do if you've seen a full box, and according to that, it either leaves or box or empty. So now we're trying to describe those situations as an ultra-pom DP. So an ultra-pom DP basically works like a zero-sum game. Right? We mentioned before that information is like a zero-sum game. Where I choose a policy, and Murphy chooses a call policy after seeing my policy. Murphy knows what my policy responds to me with a call policy. Now, where's the non-crispness? So the non-crispness affects it that we have those places where sometimes the world can explode. Like we hit a logical contradiction and the space-time continuum disintegrates, and we really like it when it happens, because this means our loss is equal to 0. So we like it, and Murphy hates it, right? Because Murphy is trying to screw us over, right? So what happens in the empty box dependent is by if you choose the policy that no matter what I will one box, or well actually it's empty box dependent, so the optimal policy, okay, the optimal policy here, since it's empty box dependent, is actually one box in here and two boxes in here. Right. This is the optimal policy. And then we will end up with 1,000,000 and 1,000. So why? Because, so first of all, it's clear that, first of all, just from the definition of Newcomb, it's really is the optimal policy, right? So whenever you see an empty box, one box. Whenever you see a full box, two box. Right? Because we know that omega is only filling the box according to what you will do when you see the empty box.
Alright.
Right? So
Okay.
right? So when you see the empty box, you need one box. When the full box, you don't care. Just go for everything you can take. So the two boxes.
Is there not a version where omega simulates in both situations? So we have like.
Yeah, we could do like logical conjunction, whatever. But let's just keep it simple to just kind of illustrate that. I mean, if it's at this junction, then it would work. If it's a conjunction, it would. So this junction would be like the good case. The conjunction would be like the best case. But, yeah. So here, why it works? Again, why it works? Because by choosing to one box here, you prevent the call policy from ever going here. Because if the call policy went here, the loss would be 0. So now the call policy, in order to avoid a loss of 0, like a complete victory for you, the opponent is forced to go here. And once the opponent goes here, you end up here with your 1,000,000 plus 1,000. So you're happy. Your strategy is play A1 and 2. The opponent's strategy, the opponent can choose whether to go to this gate or this. Here it's Murphy chooses where to go. Right? But Murphy would always, so in the worst case, Murphy would choose this. Because if Murphy chooses this, we end up here with 0. So if you go here, you end up. But here, this doesn't work. Why here it doesn't work? Because here you try the same trick. You say, okay, whenever I see, so this time, what you want to say is, okay, whenever, so in the original Newcomb problem, the correct thing is to one box where you see the full box, and it doesn't really matter what you do when you see the empty box. You can two boxes if you want, but it doesn't matter. Let's say you have two boxes when you see the empty box, whatever. Yeah, it's the same. So in the true Newcomb problem, we're supposed to end up here. Right? That's what's supposed to happen. But this ultra PODP doesn't ensure it because you chose this policy, but now the call policy, it just goes here. Okay, and now what? It's not punished. Here, it cannot like do this. The call policy has to go to the state which corresponds to the true prediction of what you're going to do in some sense. It cannot mispredict because if it mispredicts, it will get punished here. But here it doesn't get punished. it's as if you're committing to one box here, and then you see the empty box anyway, and then you go to Omega and you say, "Where's my money? I committed to one box." And Omega said, "No, you're lying. You put 2 boxes. Proof that you put 1 box. You know, you cannot prove it because the box is already empty. There's nothing you can do to prove it wrong." So in this scenario, this method doesn't work. And this is like a condition which I call zero causality, which is like a condition when this thing doesn't happen.